Hi, it's Mrs. Schmidt here. I hate missing review day, but these are the big ideas that I would have made sure to go over with you after you do the progress check. So you can watch it as you need it. We're going to do mainly focused on exponential functions and how you can tell a lot about a function from its graph and all the vocab that you have to have related to that. So remember that the parent function for an exponential function is y equals a times b, oops, hang on, to the x. And a and b are going to tell us a lot about the function. So let's just start first. If we have exponential growth, so if we know that it's going to be exponential growth by looking at the base. If we see that the base is greater than 1 and we have an a greater than 0, meaning a positive y-intercept, then we should see some sort of graph that looks like this. It's going to start, close to the x-axis. It's going to be an increasing exponential function. Its y-intercept will be 0, a. Okay, this is definitely an increasing function, and some of the vocab that you're going to see on your progress check is that it's increasing. If you thought about making those tangent lines as we move from left to right, the tangent line slopes are going to be increasing. So this is increasing at an increasing rate, which means we can also tell this is concave up. So I could ask you any of these things about this function, and I may not give you the graph, right? I might give you the equation, but if you see that the base is greater than 1, making this growth, and that the y-intercept is greater than 0, I know it's going to look like this. So before we talk about decay, let's talk about what happens if I change a and make it less than 0, even though I still want the base to be greater than 1. So here, if I'm making the y-intercept negative and there's no sort of shift in the equation, I'm basically taking this function, if a is negative, I'm going to reflect it. So I'm going to refer to this as reflected growth. And it's reflected over the x-axis, so a vertical reflection. And so the y-intercept is still a. It's just here that a is some sort of negative number, less than 0. Okay, so even though this is growth, as I trace the function from left to right, the y values are decreasing. So this is going to be a decreasing function. And if I check the concavity, this is concave down. As I look, let's do tangent lines. So close to 0, getting negative, getting more negative, more negative. The more negative, the smaller the rate of change. So this is decreasing at a decreasing rate, meaning the rates of change are getting more negative. I can see that this function is concave down. So I know that the rate of change is decreasing since the function is concave down. Okay, so now let's go do the same thing for exponential decay. All right, so exponential, actually let me go back to red maybe. Okay, so for exponential decay, Let's start with a positive y-intercept, so no reflection. And now I'm expecting to see a base that is less than 1. However, that base needs to be positive. So if this is the case, I'm going to have a decreasing function. It still has a horizontal asymptote of, or it still has, excuse me, a y-intercept of 0a. I do want to mention the horizontal asymptote. Just talking about the parent function that hasn't been shifted up or down, all of these functions, even though it's not our focus right now, have a horizontal asymptote of y equals 0. So every single one, reflected or not. The only thing that can change that is when we shift the graph up and down, the horizontal asymptote will shift with it. So a vertical translation would be the only change that can change the horizontal asymptote. Okay, so now I see a decreasing function, back to exponential decay, but I can tell it's concave up. So this is decreasing at an increasing rate. Because it's concave up, if you check your tangent lines, they're very negative, less negative, getting closer to 0 as we go. So the rate of change is increasing because it's becoming less negative. Okay, also to finish that out, if you see a problem and you see a negative a value, so I see some sort of vertical reflection, and then the base is less than 1, let's talk about reflected decay. So you'll know it's reflected because the y-intercept will be negative, or you'll see a negative outside of that base. Then the base itself will be between 0 and 1. I'm going to take the graph I just drew and reflect it over the x-axis. So still the same, the a value will be the y-intercept, but it will be a negative. And this function is increasing. However, it's concave down, so it's increasing at a decreasing rate. And if you use tangent lines, I have a very positive slope at first, less positive, getting smaller as we move from left to right along this curve. So I would suggest having at least, knowing exponential growth and decay. If you know these two, you don't have to memorize everything, but know what happens. If your a value is negative, that's going to make a reflected graph. And you can actually know a lot about the function just by the two numbers in its equation. The other thing that usually comes up the most is talking about how two different types of transformations are actually equivalent to each other, even though they don't look equivalent. So let's do an example of that next. The example, and I'm going to leave some space to do our conclusion above it, but if we have something like 2, let's say y equals, make it an equation, 2 to the x plus third, or 2 to the x plus 3 power, we can actually rewrite this using laws of exponents. So if I see one base and the exponent has addition, it's equivalent to separating it into 2 to the x times 2 to the third. Right? This is true. If we see two bases that are the same, their exponents get to add when those multiply together, the two expressions. So then I could rewrite this and say, okay, 2 to the third is 8. This is the same as 8 times 2 to the x. So you'll see several questions on that progress check were about function manipulation, just rewriting the equation into an equivalent form And what this one tells us is that this original function had a horizontal translation. So I'm going to say a horizontal translation is equivalent to, and then look at our end result. At the end, the base was 2 to the x, and it has an 8 in front, and that's a vertical dilation. And if we went and graphed these, you could kind of argue either one. You could say, well, it looks the same as if I just shifted 2 to the x 3 units to the left. Or you could say, well, no, out of context, it actually looks like it goes up much faster. So it looks vertically stretched by a scale factor of 8. Okay, so that's one type of function manipulation. The second would be something like, let me get an example. This time, let's have 2 to the 3x, and let's rewrite this into an equivalent form. So if we have 2 to the 3x, that's the same as saying, well, this could be 2 to the third to the x power. If I look at my exponent rules, it would still mean that the 3 and the x are multiplying in our exponent. And I could go ahead and simplify this and say, okay, I'm actually going to say 2 to the third is 8. So this function here that's been horizontally dilated is the same as if the base completely changed. So I'm going to go ahead and say a horizontal dilation is equivalent to changing the base. Okay, these are the two concepts right here, the transformations being equivalent, and then the shape of the graphs that I just showed on the page before. Those are the two that came up the most in the past. I'm also going to make a separate video where I literally work out every question from the progress check. It'll go in a different order, but hopefully it can still be helpful as you do your progress check and see what you need to work on before next class's test.